Okay, transforming exponential functions. Our objective for this lesson, graph and identify transformations of exponential functions. Okay, we are going to go over our previous transformations that we did, I don't know how many sections ago, when we were doing absolute value. We're just going to introduce a new parent, and that's this exponential parent that we will be doing those transformations to. Okay, so first there's basically two parent functions that we're always aware of. First is just that linear function, which tends to be just f of x equals x. It's a line with a slope of 1, a y-intercept of 0, so we just write it as x. F of x equals x, and that's our linear function. It looks like this guy right here. It's just that straight line with a slope of 1, a y-intercept of 0. Okay. Another parent function is our absolute value function, and that's our absolute value of x. Okay, so again, this is that V shape that we've dealt with before, that we transformed. Remember, we moved him up and down, left and right. That's what we're going to be doing today with our exponential functions. There is not just one exponential parent function, mainly because the base can be a lot of different numbers. But we really think of our exponential parents into two groups. Our first is our growth function, our exponential growth function, and this is when your base is bigger than 1. Okay, so our exponential growth functions, basically if we call it h of x, would be a b to the x. So there is our growth. There is our exponential parent function. But this b could be a lot of different numbers. So depending on what that b is, if that b is larger than 1, we would have a growth, which is going to look like this function right here. And if our b is less than 1, we would have that decay. If b is less than 1 but bigger than 0, so for example, a growth would be a 2 to the x. The decay would be like 1/2 to the x. Okay, so there isn't just one standard, like here there's one standard absolute value parent. Here there's one standard linear parent. There isn't one standard exponential parent, because this base, like I could have 3 to the x, I could have 4 to the x, I could have 6 to the x. Each different base is a different parent function. Okay, so there isn't one single parent function, but they all behave very similarly. Okay, first of all, our exponential parent. So here, all of this stuff we're talking about down here has to do with our exponent. Here, those exponential functions. Our exponential function's domain and range. It goes left forever, it goes right forever, so that tells me the domain is all real numbers. The range, it goes up for forever, but it only hits this bottom right here of 0. So the range, f of x is, or we can write it as y, is greater than 0. So the range of the y is greater than 0. Okay, x and y intercepts. All exponential parent functions share this point, because whenever I put in a 0, anything to the 0 power is always 1. So they always have the same y-intercept. The y-intercept is always at 1. Of the parent function. Now, if I shift it up or shift it down, that might change. But the y-intercept is always 1. And there is no x-intercept because there is a horizontal asymptote. There's a horizontal asymptote at y equals 0. There is this horizontal line that it never actually crosses. So it has that horizontal asymptote. Okay. Since it's always going up from left to right or going down from left to right, there is no maximum or minimum value. It keeps getting smaller and smaller and smaller and smaller and smaller. It never actually hits 0, but it keeps getting smaller and it keeps getting bigger for forever. Okay, increasing or decreasing? Well, if it's a growth, if the b is greater than 1, it's going to be increasing across the entire domain, increasing everywhere. Whereas the b is less than 1, but bigger than 0, it's going to be decreasing everywhere. Again, here we're just talking about the parent. These things do change as the function changes. Okay, so let's go ahead and let's do this task. This should be actually task 1. Somehow it didn't get numbered right. So this is task 1. So here we have the graph of two parent exponential functions. So these are the parent exponential functions. And we want to look at part A, which reference points allow you to determine the base of each function. What do we mean by reference points? Reference points are points we use to compare functions. Points used to compare or create a rule. Okay. For example, the most common reference points on exponential are, if we were to create a table, are the 0 and the 1. When I input 0 and I input 1. Well, we know from up here, anything to the 0 power, this first point is always going to be 1. Because anything to the 0 power is 1. Unless we move the function. If we move it up, if we move it down, if we move it left, if we move it right, it's going to change that y-intercept. So that is a reference point that we use to determine if my function's been moved up or down. Okay. And this next one, anything to the first power is itself. 2 to the first is 2, 1/2 to the first is 1/2. So this reference point helps us determine the base of the function. Again, unless I'm shifted up, down, left, right, and then we'll have to adjust for that. But which reference points allows you to determine the base of the function? The input of 1. These reference points right here. This input of 1. So that tells me that that blue function, that f function, f has a base of 2. Because the point 1 gives me an output of 2. Whereas the red function g has a base of 0.5 or 1/2. So my function, it says write an equation for each function. So my f of x would be 2 to the x. And my g of x would be 0.5 or 1/2 to the x. 0.5 to the x. Okay. What reference point is shared by all parent exponential functions? Well, that would be, we talked about it over here, that would be that point 0, 1. Because if we're talking about the parent, it's not talking about moving it up, down, left, and right at all. So it would be that point 0, 1. Why? Because anything to the 0 power is 1. Okay. Which one is growth? Which is decay? Well, my blue one has a base of 2, so f of x is growth. Why? Base is greater than 1. And g of x is decay. Since b is less than 1. Now, this next bit. What are their growth and decay rates? The growth and decay rates is how much more than 1. Remember, our rate comes from that 1 plus r to the x or 1 minus r to the x. Okay. So for my blue one, my base is 2. So remember, f of x equals 2 to the x. So basically 1 plus what to the x is the same as this guy here? Well, 1 plus 1. So my growth rate is 1, or that would be 100%. So this one doubles each time. It grows by its full amount each time. So the rate is 1, or as a percentage is 100%. Whereas the red one is 0.5 to the x. So that's decay. So 1 minus what is 0.5? Well, that would be 0.5. So that one's rate is 0.5, which is 50%. So this one decreases by 50% each time. So we have a growth rate of 100% for f of x and 50% for the red one, g of x. Okay, now that we've discussed the parents, let's translate these guys. So these translation rules are the same as the ones we did before. Okay, I'm pretty sure, let me find right here, chapter 8. Oh, let's go up. So here, this is section 8.2 from way back when. So here, translate. We're translating up and down. We're translating left and right. The rules are the same. The only thing that's different is the parent function. That's the only thing that's different. Okay, so if I want to translate vertically up and down, the rule's the same. I take the function and I add c or subtract c. If I add c, it's going to move it up c units. If I subtract c, it's going to move it down off the end. So if I'm looking at the graph, let's go ahead and let's just graph. Let's graph as just standard. Let's go ahead, let's make this growth parent. So there's my parent f. Okay, and let's say, I'm not going to put a scale on this, but let's say this blue one is f of x is 2 to the x. So if I take this function, this 2 to the x, and add 5 to the end, it's going to take this function and move it up 5. And so now I'll have one that looks like that. It moved it up 5. Okay. So by adding 5 onto the end, it's going to take that whole graph, move it up 5, and there's my g. Okay. Again, the rules are the same. We're not having to memorize new rules. Horizontal, moving left and right, still works backwards. And it works inside the function. So f of x plus c is actually going to move that guy left. F of x minus c is going to move it right. So again, if we stick with the same parent function, let's just do 2 to the x. Okay, again, I don't have a scale to it. Just kind of like that. And I want to move it to the left to get a new function. How this one's going to look, it's going to be 2 to the x minus 3. Notice how that negative 3 here is up in the exponent because it's inside the function. It's in on the x. So that's actually going to move it right 3. So now it's going to take this function and it's going to move it right 3. So it's now going to put it over there. Pretend it's just a steep. So this moved this point right 3. 3 right to get g. I kind of just ran out of room. I should have moved them left. I would have had more room that way. Okay, so adding or subtracting in there is going to move it left or right. Okay, so let's go ahead. Let's jump down. We're going to talk about stretches, shrinks, and reflections here in a minute. Let's jump down here to task 2. So here we have a graph of a parent exponential function. It's 2 to the x. So we're dealing with that 2 to the x function, along with the graphs of 2 other exponential functions. So we have g there in red and h there in green. Describe how the graphs of g and h are transformed from the graph of their parent. Okay. So if we let's look at these reference points. This 0 to this 0, this one goes, for the red, this one goes up 4. We're at 1, up 3. Now let's check the other reference point. Let's check the 1 to the 1. Does that one also go up 3? 2 to 5, yep. That one went up 3 as well. So it looks like G is going up 3 from the parent. Okay. Now let's use those same reference points for H. This one at 0 was up at 1. It's now down 2. It looks like it went down 1, 2. This one went down 3. And let's check that other reference point at 1. Did that one also go down 3 from 2? That one also went down 3. So describe how, G is up 3 from F, and H is down 3 from F. So to write the function for G, I need to take f of x and move up 3. Well, what is f of x? F of x is equal to 2 to the x. So my function g to the x is going to be equal to 2 to the x plus 3. Whereas my function for h of x, I need to take f of x and go down 3, subtract 3 to move it down. So my h of x is going to be 2 to the x minus 3. And then at this point, we can always double check them to make sure that they worked. Desmos is a great tool for this. I can graph f of x equals 2 to the x. So there's my parent. And I can even double check those points, like the point, and plug in those reference points, like the point, oh, new line, like the point 0, 1, and then what was the next point? 1, 2. There's those reference points. And now I can label my next function, g of x. And that one we decided was 2 to the x, out of the exponent, arrow over, plus 3. Yeah, and it looked like 0, 4 was a point, and the other point would be the point what? What was it? 1, add 3, so 1, 5. Yep, that point worked as well. So we can check these. And I can even change the color if I want to make a match. So you hit that cog up there and you can change the colors to make them match the graph, just to make sure that it does in fact match. Identify the domain, range, and end behavior of each function. Explain how the transformation affects these characteristics. So first, let's go ahead. Let's look at f of x. Okay, f of x, domain, all real numbers. Range. Actually, let's create a little table. Range, y is greater than 0. We're still greater than 0. End behavior. What happens as x gets really big and as x gets big? Meaning, as x goes this way, what's my function do? It goes up. My function, as x gets big, f of x also gets big. As x gets small, meaning go this way, what does my function do? My function gets really close to 0. My function goes to 0. So there's for f of x. Okay, how does that happen? How does that affect g of x? Is g of x any different? The domain is still all real numbers. What about the range? Does it go from 0 on up? Nope. Instead of 0, its asymptote here is at 3. So it goes from 3 on up. The range is greater than 3. So moving up and down does affect that range, which makes sense. Range is up and down. Okay. The end behavior, as x gets big, okay, as we go out this way, my function is going to go up, right? So as x gets big, my function, oh, not f of x, g of x gets big. And as x gets small, negative infinity, g of x, it doesn't go to 0 anymore. It's going to level out and go to 3. These kind of correlate. This guy and this guy are going to relate to each other. Okay, our very last function, we have that h of x. I kind of have room. Let's squish them up here. The domain is still all real numbers. The range is now, instead of positive 3, it's going to be the negative 3, because there's my asymptote. Y is greater than negative 3. And then as x gets big, g of x gets big. Oh, I keep doing that. H of x gets big. And as x gets really small, negative infinity, h of x is going to go to negative 3. Not positive 3 or 0 like the last two. So moving up and down does affect that range and the end behavior. It affects the end behavior to the left in this case. Okay. All right, so we talked about vertical and horizontal translations, moving left and right. Now let's go ahead and let's deal with vertical stretches and shrinks. What the book also calls them compressions. So a compression is just a shrink, compressions, stretch, and compressions. So compressions happen by multiplying the function. So if I take a function and multiply out in front, if this a is greater than 1, it's going to be a stretch. If that a is less than 1, but bigger than 0, it's going to be a shrink or a compression. Okay, so how that will look, if we look at our parent, again, I'm going to keep using this 2 to the x, again, not to scale. Okay, so if I stretch him farther out, so let's go ahead. So here's my function, f of x equals 2 to the x. So if my new g of x, let's change color, is 3. times 2 to the x. It's now going to make it 3 times as far. So this little distance is now going to be 3 times as far. So whatever this distance is, I now go 3 times as far. So it'll be 1, 2, 3. So now here's my new point. This one, this distance is now going to be 1, 1, 2, 3 is now going to be that. So it's like stretching these out. Okay, so it's going to be 3 times as far. So it is going to affect, but eventually it's still going to come down and get to this asymptote. So it's still going to have that same asymptote. It's just going to take longer to get down there. Okay, because we stretched it 3 times as far. So it's going to make those spaces a little bit bigger. So like this point from here to here, so this distance is going to be 3 times as far. 1, 2, 3. Okay. So that is our stretch, and then a compression again would make it half as far. Like let's say I have 1/2 times 2 to the x. That's going to make those distances half as far. So it's going to make it not grow nearly as fast. So there's our stretch and shrink. And our last one is our reflecting over the x-axis, and that's if it's a negative. So if I have a negative times f of x, so basically if I have if my g of x equals a negative times 2 to the x, so a lot of times it'll like that, negative 2 to the x, that's going to reflect it over the x-axis. So it's going to take my parent, sorry, I don't know why I went to eraser. And again, if we deal with my f of x is 2 to the x, there's my parent. The reflection here, this g of x reflection is going to do that. So now it's switching it from an increasing to a decreasing function. It's not going to affect my domain, but it is going to affect my range, because now we're looking at the numbers less than 0 instead of greater than 0. Okay. All right, so let's do a couple more tasks. Okay, so here's task 3. 3. So here we have the graph of a parent function, again 2 to the x there in blue, along with the graphs of 2 other exponential functions, g and h. Describe how the graph of g and h are transformed. So let's go ahead, let's look at g first. G is there in red. So we're going to look at those reference points again. This is the reference point 0, 1. This is 0, negative 2. Now we might, if we were just looking at that point, we might like, oh, this goes down 1, 2, 3. But if we look at the next reference point over here at 1, this one and this one does not go down 3. This one does not go down 1, 2, 3. Okay. This one is in fact it flipped it over. It's a reflection. Now, did it reflect it the same amount? Like this one's up 1. This next one would have to be down 1. It didn't. It's now twice as far. So not only did it reflect, it made it twice as far. So then we also measure the other thing. So this one, it reflected down. So G is a reflection. So I know I'm going to need a negative. So I know I'm going to have negative 2 to the x. But just a negative 2 to the x would just move it down here. And then it would just move, since this point's up 2, it would move it down 2. It would just be down here. But since if we look at this distance, and this distance is actually twice as far. So that tells me that's going to be a stretch, a reflection, and a stretch by a factor of 2. Okay, so a stretch by a factor of 2. Okay, so we're not actually writing the equation yet, but G is a reflection and a stretch by a factor of 2, whereas H does not have that reflection. Let's go and let's erase a bunch of my marks there. Okay, H is not a reflection because we're still up. And we might again be like, oh, it just shifted it down like a half. It didn't, because this one isn't shifted down just a half. If we zoom in, this one is half as far. This distance was 1. This distance is 2. It's half as far. So that tells me that that's a vertical shrink. So H of x, vertical shrink. By how much? By a factor of 1/2. And why we say factor is it's a multiple. We're multiplying by 1/2. So each of these functions for my g of x, I need a reflection, so I need a negative, and I need it twice as far, so 2 times 2 to the x. So there's my reflection in that negative, and there's my 2, my stretch by a factor of 2. And then now my h of x is just that shrink by 1/2, so 1/2 2 to the x. And again, you notice how I put my parentheses just to keep my base separate from my stretch or shrink. And then we could jump to Desmos at this point and type them in and make sure they work. So there's my 2 to the x, so I could type in my other one, g of x equals, and what did we just say, negative 2 times 2 to the x. There, yep, that looks like it. Okay, so we always want to double check there with the graph. So we want the domain and range and end behavior of each function. Explain how the transformation affects these characteristics. So we already did the domain and range of f of x. It's up here. All real numbers greater than 0. So now for g of x, they're in red. This is now a decreasing function that doesn't affect the domain. The domain is still all real numbers, but my range, instead of greater than 0, it's now less than 0 because it's now below here. And it does affect my end behavior because here as x gets big, g of x gets really, really small. It goes to, not equals. It goes to negative infinity because it's going down for forever. And as x gets really small, meaning as we go this way, my function gets really close to 0. G of x goes to 0. Whereas for h of x, not a whole lot has changed. My domain is still all real numbers. My range is still greater than 0 because I'm still up here. And my end behavior, as x gets big, so does my function. It's still increasing. And as x gets small, my function still goes to, I shouldn't use f of x. Oh my goodness, I need to stop doing that. This should be h of x. Sorry, guys. H of x, again, goes to 0. So really, just a plain stretch or shrink doesn't affect any of that stuff. It doesn't affect domain, it doesn't affect range, and it doesn't affect end behavior. It just makes it go a little slowly, more slowly, or faster. Okay. In this case, it's going to grow slower than the parent, but it's still going to grow. How can you tell whether a function is increasing or decreasing? Explain. Does it go up or down from left to right? That's really our gist. We read a graph from left to right. Is my graph going up or is it going down as I read from left to right? Okay.